So today we are going to talk about optimal, stochastic, non-smooth, non-convex optimization through online to non-convex conversion. Okay, that's a lot of words. So let's get into it. So non-convex global optimization is NP hard. Okay, so we cannot actually hope to find a real minimum. We can actually hope to find a stationary point. That is a point such that the gradient at that point is less than some small number. So previous results are, which they will support here, is for smooth non-convex functions, SGD takes epsilon minus 4 iterations. For second order smooth, SGD takes epsilon 3 to the minus 3.5 iterations. And it makes sense because second order has some more structure. And why epsilon to the minus a negative power is because the smaller you make epsilon, the more rigid you are on your function, that I need it to be really small. So it takes inversely proportional to epsilon. So the problem is that ReLUs, max pools, neural networks, they cannot be smooth. So it is entirely possible that for a desired point, the gradient norm doesn't even make sense. Like the gradient doesn't even make sense at that point. So instead, what we will return is a delta epsilon stationary point. What is a delta epsilon stationary point? If I have an almost differentiable function f, there is a finite subset S in a ball of radius delta around x, such that if I select y randomly from that finite subset, I get the expectation of y as x, and I get the gradient of y, the expectation is less than epsilon. So the thing is that at such a y, it is going to be differentiable, because it's an almost differentiable function. So gradient at y, that exists. So another definition of this is, given a point x and a number delta and an almost differentiable function f, I get the gradient f delta ball is the infimum of all finite subsets such that they are centered at x in a radius of ball delta, and this is basically the average of the gradient at that point. So the final goal will be to bring the RHS, just this part, down to epsilon, and the infimum is always less than that quantity. So we have found a delta epsilon stationary point x. So another way to look at this could be, instead of going from left to right, let's go from right to left. Let's say I found some points S, and the gradient average norm of those S points is less than epsilon. And I know that the delta norm is defined as the infimum over all such points. So whatever S points that I have returned can only be greater, the RHS quantity can only be greater than the infimum quantity, right? So if I bring this RHS down to epsilon, I have found a delta epsilon stationary point, which will be the average of those S points essentially to satisfy this condition. Next is the stochastic gradient oracle. Our algorithms access information about the function f through a stochastic gradient oracle grad. So it goes from a Hilbert space to a Hilbert space times the input IID to Hilbert space. So given a point x in that Hilbert space, the oracle samples an IID random variable z and returns the gradient, like the stochastic gradient at that point z, such that the expectation of that gradient is the real actual gradient evaluated at that point x, and the variance of that gradient is less than sigma square. So it's basically, it has an expectation and a variable. So it's a random variable, this grad. So now we define a well-behaved function. So if we define a differentiable function f going from Hilbert space to real, let's say, to be well-behaved, if for all xy in the input space, it holds that the difference between f of I and f of x is the integral of the gradient on that path between y to x. So when t is 0, this is gradient at x. So I integrate the gradient from x to y on the path y to x. And if that is equal to f of y minus f of x, then it's a well-behaved function. It's like saying it's a conservative field in physics, you know. So if f is differentiable everywhere, it is well behaved. That's just calculus, right? You take the integral of the gradient on the path from between y to x, and it's going to be f of y minus f of x. What if it's not differentiable? If f is not differentiable everywhere, we're going to make some changes to f. We're going to find a function f hat which is a little bit perturbed. Like if I give you a small number p, what you're going to do is expectation of u, where u is a random vector of x plus pu, right? So now just trust me, bro, on this one, that f hat is differentiable and well behaved. The oracle, how would we define the stochastic gradient oracle for this f hat? It will be the gradient oracle for f, but in some direction u, where I just pick u randomly and go in that in the u direction of by length p, and evaluate the stochastic gradient of f at that point. And you can see that if I put the expectation over here, the expectation gets rid of the u, because it's like uniformly distributed in a ball, randomly distributed, right? So it's actually the stochastic gradient oracle is the stochastic gradient oracle for f hat as well. So moreover, if f is differentiable, f is differentiable at x plus pu with probability 1, because it's an almost everywhere differentiable function. This follows from Rademacher's theorem. For a Lipschitz continuous function, points of non-differentiability have measure 0, just as rationals are measure 0 among real. So basically all I'm trying to say is, if I make a perturbed function and let's say I'm at a point of non-differentiability, instead of just trying to get the gradient at that point, what I do is move a little bit away from there. I can be really sure that now I'm going to be differentiable, and I take the gradient at that point. If f is G Lipschitz, then f hat, then what this statement is saying, that my perturbed function f hat is not too far from the real function. So this is what it would look like. Let's say for mod x, the mod x is non-differentiable at 0, and now we have the perturbed function x plus p, x minus p, so it's u is plus 1 minus 1. So now this function has a gradient defined at 0, which is 0, because it's like the average of the gradient and the left on the right and left hand side. So basically all this is trying to say is, at points of non-differentiability, just give it a gradient which is like the average of the gradients on all ball around it. So now the online convex optimization part. So online convex optimization is a process where we stand at xn minus 1 and jump to xn, right? That's basically it. So for first order algorithms, we see that the f of xn minus f of xn minus 1 is, from Taylor expansion till first order, equal to the gradient evaluated at xn multiplied with inner product with the step, or the gradient evaluated xn minus 1 inner product with the step. If we want to fit an online learning scenario into such a problem definition, we would want to minimize the gradient at xn. Why? Because if you're trying to minimize this gradient at xn minus 1, we already know xn minus 1, like the gradient at xn minus 1. Let's say we knew it. We want to pick a delta n such that I am able to minimize it through future. That's what online learning does, right? We are trying to give vectors such that whatever loss function my adversary returns to me, I can have a small regret in like I'm trying to predict the future. So delta n should be chosen to minimize the inner product between gradient at the future point, which we do not know, which will depend on delta n actually. So over some rounds. So why do we want to minimize it? Because by minimizing it, I'm making sure that I'm taking the biggest step in the loss. And if I do it over n rounds, I take minimizing steps over n rounds, so I will get to a point which has a low loss, low f value, right? That's what we're trying to get to. So some problems. We don't really know the real gradient, only the stochastic gradient at any of these points, right? So the answer to this is like double down on randomness. That is, we evaluate the gradient gn not at xn minus 1 or xn, which will be the next step which we get to, but at a random point in the middle. So for a well-behaved function, f of xn minus 1 minus f of xn minus 1 was f of xn minus f of xn minus 1 is the expectation of the inner product of the gradient and the step that we are going to take. Why? Let's look at the definition. The expectation of the gradient is actually gn evaluated at all points between xn minus 1 and xn, right? So this the delta n is y minus x here, and the gn is expectation over Gn is the stochastic gradient evaluated at any random point in between x and y. So take that integral, and now stochastic gradient in expectation is equal to the gradient of f. So basically this expectation is just not only over some random point between x and y, it's also an expectation over the stochasticity of the gradient oracle. So it's like a double expectation. So minimizing the inner product between Gn and delta n is like predicting the future, and that's what I said about online learning. Like that's where we will bring online learning. Now another problem is, because everything in our problem definition is so random, if we want to return one final point as an answer to the optimization, we could be really wrong, because we only have stochastic gradient evaluations, not real gradient evaluations. So finance 101 is, when in doubt, diversify. So instead we will supply k points, each of which will satisfy the stationary point conditions in expectation. Basically what it's trying to say is, each of those k points will have a small delta gradient norm. And by diversifying, we have mitigated some risks. So the algorithm is, run the online learning for t steps, do some averaging on those t steps, repeat this for k buckets, and return k points from which we will sample randomly to keep any adversary at bay, right? So this is the algorithm. We have an initial point x0, some k which is a hyperparameter, let's say, a t which is the number of steps in a bucket, an online learning algorithm A, Sn is just a random point between 0 and 1. And we need this because we are going to evaluate the stochastic gradient at a random point between xn and xn minus 1, right? So let m be k times t, basically how much rounds of online algorithms we need to do. So k buckets times t iterations. Get a delta n from algorithm, the online learning algorithm A. Set my xn to be xn minus 1 plus delta n. So take that step. Now set my wn to be xn minus 1 plus some random number between 0 and 1 times delta n. So wn is a random point between xn minus 1 and xn. So now if I sample a random zn, or zn could be given to be by adversary, who knows, generate the gradient gn, which is the stochastic gradient evaluated at wn on the input point. Now wn is the random point between xn minus 1 and xn. So this is a random gradient at a random point. So double down on randomness. Now send this gn to a as the gradient to get the loss function going. Right? So now that's how it works. Now what we have is, forget line 10 for now. Let's look at line 11. What we will do is, for k buckets, I will set w bar k to be the average of those t points in that kth bucket, right? So w sub t, k, fix a k. This is those w points which my algorithm visited in this kth bucket. Take the average of it and store it as w bar k, and return w bar 1, w bar 2, w bar 3, etc., etc., etc. for all those k buckets, right? That's what it is. So I've returned k points, and where each of these points are an average of these t points which the algorithm visited, right? So now we need to define this k shifting regret. Now why do we need to define that? Because we are resetting our algorithm every t iterations for k times, right? So I need to be able to give k some regret guarantee based on k. So what I have is regret between gn and the delta n minus uk, where u superscript k is the minimizer in that kth bucket. It's pretty intuitive to know that if it's pretty intuitive to see that if I reset my algorithm for k times, my regret can be like, it's going to be k times basically. So intuitively I'm not gonna, but it makes sense to have the shifting regret of order k root t, right? It makes sense. So now I'm going to go into a theorem now, which is going to be a little bit equation-y, so bear with me. Let me define an average gradient of nth point, which is the gradient evaluated at some point between xn minus 1 and xn, and I take the expectation. So this is the average gradient on the path between xn minus 1 and xn. So if my function is well defined, f of xn minus of f of xn minus 1 is the gradient at the random point on that path, right? But this is, let's say, delta n returned to me by my algorithm. So this is I can disregard this, and I can take the integral inside here. So this becomes basically what I'm trying to say is that f of xn minus f of xn minus 1 is the average gradient times this step. Now I want to focus on gn's because that's what our loss vector is. So I add subtract gn and I add subtract un, which is the minimizer term. And why did I do that? It's pretty simple, because this is now a regret of my online learning algorithm. This in expectation will be 0 because expectation of gn is the average gradient between xn and xn minus 1, right? Now this term is what we have to focus on. This is regret, we can bound regret. In expectation this is 0. Let's look at the third term. So by telescoping, basically taking the sum over m iterations and taking the expectation, f of xm will be f of x0, like bringing the f of x0 here, plus expectation of the regret from the first term, expectation of this will become 0, and expectation of gn un, right? Alright. So what was an online learning algorithm? The online learning algorithm is, let's say, convex at C. I predict my WT in C. I receive a convex loss function in which in this case is the inner product with gn and WT basically, and I incur the loss. So the loss incurred is inner product with gn and the step I take. So my PGSD, the subgradient descent rule was the delta t plus 1 will be projected over some C, delta t minus the gradient of my loss function evaluated at t. What is the gradient of my loss function evaluated at a delta t? Because it's a linear, my gradient is gn actually. So my algorithm becomes delta n plus 1 is projected over what I'm setting my set C to be is a ball of radius d. So projected over this ball of radius d, delta n minus eta times the gradient gn, which is the gradient of the loss function, but it is actually the stochastic gradient evaluated at point wt. Like that's a crucial thing to note here. And now expected regret is k d g root t, where d is the size of this, g is the norm of the gradient, and root t is, and k is the k balls that we are looking at. Now this looks like an SGD with momentum, with clipping. Why? First of all, clipping is obvious, like we clip the step to a norm ball of size d. Why is it SGD with momentum? My next step is the same as my previous step minus a little bit, minus a little something, right? So this is like I keep on moving in that same step with some updates. So higher the eta, lesser the momentum. Lower the eta, more is the momentum, right? Except one thing, that the gradient is evaluated at a random point in between instead of the endpoints. In SGD with momentum, you would think that I would evaluate it, let's say, at xn or xn minus 1. But here gn is evaluated at a random point. So now how do you choose, let's say I fix k. I'm in the kth bucket. Now I'm going to talk about the kth bucket. I run the algorithm for t iterations. So how would you choose uk? So the vector u superscript k is chosen to minimize the sum. Like this is the argmin of that loss function, right? For those t iterations. Or because uk is a fixed vector, I can equivalently take, because it's a linear thing, I can take it inside the sum. To achieve this, I could choose u superscript k to be absolutely opposite to the direction of, the sum of the vector g, sum of the gradients, right? But I don't really know g gradient. I don't really want to work with this randomness. What I will instead define my u superscript k is to be the sum of the real gradients. I don't know what those real gradients are, but let me define it such a way. If this uk is not the minimizer, it doesn't matter, because my regret can only be lesser when I choose some other arbitrary u superscript k, right? Other than the argmin one. Side note, but whatever. So I define my u superscript k to be the sum of the actual gradients evaluated at those t points when I'm in a bucket, normalize it with its own length and make it of length d, basically to make sure that this is of length d. So it ensures that u superscript k is absolutely opposite in the direction of the gradient, sort of in expectation, because this is stochastic gradient and I define uk to be the real gradient, but sure, and has a length of, let's say, capital D. Now my expectation x of m is f of x0 from here plus regret plus this term gnun, right? gnuk, whatever. So regret I know, f of x0 is whatever initial point, I can evaluate it, I can ask the algorithm, whatever. Now I need to bound this thing. Now I have defined my u superscript k to be the d length in the opposite direction, and expectation of gn is the gradient and variance of gn is sigma square. What we will do is add subtract the actual gradient here, like gn add subtract the actual gradient, so the actual gradient times uk here and the difference between the actual gradient and the gn, and I can take the norm and I can put that inequality. It's straightforward. Now what I see is that for t iterations my gn and gradient, because they are the standard deviation of gn from the gradient can only be sigma. For t iterations this can only lead to sigma root t. For k maximum k buckets and d is so my right hand side can be bounded by d, k is from the sum, and for t iterations if I increase this it's going to be sigma root t, right? And this term here is sum of gradients times inner product with a vector which is again sum of gradients in the opposite direction with some normalizing number, right? So this is sum of gradients square, but then that normalizing number cancels the square, and this becomes the average t. I multiply and divide by t, 1 over t, the gradient at those t points that I have visited times d, and this d comes from the length of this. Basically what I am doing is substituting uk here. That's exactly what I am doing. Now let's look at this for a moment, right? What this means is I have found some t points such that the I am taking the average of those gradients at those t points when I'm in the k bucket. This reminds me of something. This reminds me of the delta epsilon stationary point. So I have found some t points, I have the gradient sum of those t points, and now what I can say is if I can somehow bring it down, bring this number, this quantity down, the one between the norms, I am able to comment on the delta ball gradient norm of the average of these points, because this has to be satisfied, right? The average has to be satisfied. But the average is what we are returning in our algorithm. That's what we return, the average of those t points. So I am on to something here, it seems. So now if I take this on the right hand, take this over this side, bring the f of x of m, which is always going to be greater than whatever the lower bound is, the global minima. I rearrange these terms and I divide by m, which is k times t. I get something like this. So expectation over 1 over k, I divided by k here. Expectation over 1 over k, the sum of the gradient of those t points of k buckets. It is always going to be less than this difference between the initial point and the absolute minimum, the regret, and sigma root t. Sigma root t comes from here. Sigma divided by root t comes from here. So how do you choose a ball D now? If I choose my length D to be delta over the time steps t, what I can ensure is when I'm in my kth bucket, even if each step is as far as possible, which is each step is length d in absolutely one direction, even in the worst case, the tth point and the starting point can only be delta far from each other, because d times the time step t can only be delta. So my initial point and the final point can only be delta away from each other. That means if I take the average of these t points, all of them will lie in a delta ball of that average. That's what this says, that my t points in my kth bucket can only differ from the average of those t points by delta. So now this term 1 over t whatever the sum of the gradients, basically the average of those gradients, is always, so basically it's in the delta norm definition, right? So these t points can only be greater than the infimum of any set in the delta ball, and therefore I have found a point w bar. If I can bring this right hand side down to epsilon, I have found a point w bar which is a delta epsilon stationary point. If I can bring it down to epsilon, and I can bring it down to epsilon just from my bounds basically. So now if I have a collection of, let's say, k points, I select one randomly. So expectation over that whatever random point I select is basically 1 over k of whatever the random points I will select, the delta ball, delta norm, delta gradient norm. And this is going to be less than 1 over k times the average of the t basically from here. I pull this result and I put it here. So now I have sorted everything out. I have returned k points from which I will select one randomly, and I can be really sure that the delta gradient norm is going to be less than this quantity plus this quantity plus this quantity. Now let me put some values in. So this, I put d is delta over t. So this becomes delta over t, whatever the initial point and the global minimum, the difference was. I put my regret as k dg root t, and then this is my standard deviation of the gradient of the stochastic gradient from its average, but it's always less than the norm of the stochastic gradient, right? So let's look at this. D cancels, and n over k is t because n is kt basically. So I get this. So this plus this, I use the AMGM inequality. A plus b plus c divided by 3 can only be greater than equal to the cube root of them. So if I optimize my t for the minimum, like I optimize my t such that they are the absolute minimum, then this inequality should hold. And so this is what it results in. That in such a scheme, I give a point w hat which has a delta ball norm less than some constant times g to the 2 by 3 times this 1 by 3 times this. If I enforce it to be less than epsilon, I can take the cube, I can bring n to this side, so it becomes 1 over delta and 1 over epsilon cube. That's the desired result. So my number of calls to the grid, like I need to be able to make order 1 over epsilon cube and 1 over delta times that. I need to be able to make these many gradient oracle calls if I aim to find the delta epsilon stationary point. Now what they say is, like, just this was the meat of the presentation done, and now it's just going to be a little bit more. So what happens is, if we run the online gradient descent with separate learning rate for each coordinate, we can find better results. Not better than this, but like better in terms of constants and stuff. We define all stationary points with respect to the L1 norm. Intuitively, this approach is not too bad because it allows for adaptive learning rate tailored to each coordinate, which can improve convergence. The projection ensures that updates remain within a bounded region, right? And the L1 norm encourages sparsity, which can be beneficial in high dimensional settings maybe. Now, if my stationary points are like, let's say I have smooth, let's say I'm given smoothness. So let's say f is h smooth. Now I want to recreate those results that I mentioned in the introduction. So let's say f is h smooth, that means gradient is h Lipschitz, and my point satisfied that the delta ball is less than epsilon. That means that if I were to move that delta distance, I can only go h delta, like my gradient is going to be Lipschitz, right? H Lipschitz. So my gradient of f of x can be at max epsilon plus h delta. If I set my delta to be epsilon by h, I have found a 0 epsilon prime stationary point in 1 over epsilon to the minus 4. And epsilon prime will be, let's say, 2 epsilon in this case. So up to constants, I have recreated the exact SGD guarantee. Now if it is second order smooth, just trust me here that the gradient of x is less than equal to epsilon plus j by 2 delta square, where j is the operator norm Lipschitz condition here. Now if I set my delta to be square root of t, square root of epsilon over j, I found it in like 1 over epsilon, delta becomes square root, so e to the minus 3.5 steps, which was what the ideal SGD guarantee was. Now another thing is that this is also a lower bound. Now if this comes from another paper, and what they are essentially claiming is for any function f, I can find a smoothing function and I can find a stochastic oracle which takes big omega of gamma like delta epsilon, where gamma is what? Gamma is this distance. Gamma is this distance actually. So it takes lower bound in the same quantities, like 1 over delta epsilon cube, 1 over delta epsilon cube essentially. So what I'm saying is that I have found an upper bound and I have also found a lower bound from this paper, and therefore I have like optimality. So let me go to the first page. Optimal, that was something that I hand waved on. Stochastic, because we only have stochastic gradient. Non-smooth, from non-smooth we did to the smoothing conversion by just blurring our vision and smoothing out kinks, let's say. Non-convex optimization. Non-convex optimization is that we were only interested in returning delta epsilon stationary points. And online to non-convex conversion is just an analysis technique. There is no algorithm as such here, but it's an analysis technique where we analyzed the non-convex SGD, randomized SGD through the lens of a online learning algorithm. And therefore we have found, like, this is to find a delta epsilon stationary point, we have found the optimal number of iterations needed.